All right, open up your book to section 8-5. We're on page 416 in your book. And the title of this section is the sum and product properties. The objective here is to transform a sum of two sinusoids to a product of two sinusoids, and vice versa. Let's start out with an example here. They give us an example on page 416 that asks us to graph the following function. So y1 you can see is a product of two sinusoids. And from the work we've done in the previous section, we understand that that's going to give us a amplitude that varies here when we sketch this, because it's a product. y2, here we have a sum of two sinusoids, so we have an understanding that that's going to give us a sinusoidal axis that varies when we graph this sum. So let's go ahead and grab our calculator and punch that in. So in your y equals menu, let's put in the first equation here, which was the cosine, 2 times the cosine of theta, or x for me, and then cosine of 11 theta. I got to type that in as x. Let's graph that one first here. Let's change our window. Since it's got cosine of theta in there, let's go from 0 to 360, so we'll get one full cycle of that function. And probably if we go from, let's say, -3 to 3, it looks like will be a decent window here because of that 2 out front. Should have an amplitude of 2, we'd expect. All right, so that looks pretty good. Let's change this to degree mode here. I'm in radian mode. Okay, should be all set to graph this. Yeah, that's exactly what we'd expect to see there. Our analysis that we had in the last section tells us that we should expect to see some graph here of a function whose amplitude is going to vary. So that looks good. Let's try the second one here. I guess I'll leave that first one in here. I'll just shut it off. Let's graph the cosine of 12 theta plus the cosine of 10 theta. And we should be able to do this in the same window here, so I think I'll leave that the same. But again, this is a sum, so we'd expect to see our sinusoidal axis is what we'd expect to see is going to vary. Huh. That's probably not what we were expecting to see there. Because we got a function whose amplitude is varying. In fact, that looks a lot like the function we just sketched. Let's go back to our y equals menu. Let's turn on y1, and let's graph that. Oh yeah, check that out. They're exactly the same. We have a product in one case and a sum in the other case, and it turns out we get the exact same thing. Let's grab a picture of that. So probably we did not expect to see that we were going to end up with the exact same thing. In fact, I would guess that's the case here. And I guess the question is, well, why is that the case? Well, the note captures that for us here, so let's talk about what it says here in this note. It comes down to the periods of these two sinusoids that we're looking at. That in the first case, when you look at the cosine of theta and the cosine of 11 theta in y1, cosine of theta has a period of 360 degrees. 11 theta, that would have a period of 360 over 11, which is what, a little more than 30 degrees. So those are quite different periods there. That's what it says in the note there. Note that the product of those sinusoids has very different periods, 360 versus 30. And now I can see why, when I go to sketch those functions, whether it's a sum or a product, that I would either be oscillating back and forth around that larger period function, or that larger period function would be enclosing that, or there would be the amplitude of that smaller period function if we were finding a sum versus a product there. But in y2, I've got two sinusoids that have very similar periods. Cosine of 12 theta, the 360 over 12 is what, 30 degrees? And 10 theta, 360 over 10 would be 36 degrees. So you've got two sinusoids here with periods of 30 and 36 degrees. And if you were to graph those, I think you'd see why you won't have one function that's oscillating back and forth around the other function, or there wouldn't be, if I was finding a product there, that it wouldn't be the case that I would be enclosing the other function with that larger period function. That's because of the fact that those two periods are very similar. Now you can dig a little bit further in this and play around with those four functions if you want to see this exactly for yourself there to understand why that is. But I guess the bigger question for us is it appears, though, there's a way to go from this product that I have in y1, a product of two sinusoids, and I can rewrite that somehow as the sum of two sinusoids, like y2. These two graphs were equal to each other, so there must be some way that I can make that connection between these two, that a product and a sum can be rewritten the same way there. Well, here we go. That's the first set of properties to talk about, is to go from a product to a sum. We'll talk about 4 of these. And then the other half of the discussion is going from a sum to a product. So let's start with these product to sum properties. And the first one here that we have is that the cosine of theta times the cosine of A times the cosine of B is equal to 1/2 of the cosine of A plus B plus the cosine of A minus B. Now, if you compare this with the property they give you in the book there, you'll notice that in the book they actually put this 2, I'll write it that way for you. They actually write the 2 out in front of the cosine of theta cosine of A times the cosine of B. I want to keep making that a theta for whatever reason. And they don't have this 1/2 here. All I've done here is I've divided both sides by 2 or multiplied by 1/2, however you want to say that, is how I'm getting the 1/2 over there. You can do this either way. It doesn't really matter which way you do it. You're going to get the same result or the same property here. This, to me, looks more like a product to sum property, though, because you're starting out with a product of two sinusoids that you have on the left side, and you're rewriting it as a sum over there on the right. Versus if you have the 2 out in front, that looks more like a double product property, okay, because you're doubling that quantity. Anyways, you can write it whichever way you want. You get the same result. All right, we're going to go through the proof. We're actually going to only prove half of these properties here. Once you see how to prove one, it pretty much shows you how you're going to prove the others, so I don't think we have to go through all 8 of these proofs. But the way to prove this is to start with what we have over there on the right-hand side, and then we're going to use our composite argument properties to do this. So I'm going to start out with 1/2 of the cosine of A plus B, and then plus the cosine of A minus B. All right, so that's what we're starting with. Start with what you have on the right side. And then we're going to replace the cosine of A plus B and the cosine of A minus B with their composite argument property. So we still have a 1/2 out front. Cosine of A plus B, that's the cosine of A times the cosine of B, and then it's minus the sine of A times the sine of B. That's the first part of this. Maybe I should actually put that in parentheses here just so we can see that that was the first part. Oops, we're adding these together. And now do the cosine of A minus B. Replace it with its composite argument property. It's the cosine of A times the cosine of B. But this time it's going to be plus the sine of A times the sine of B. That right there is our substitution using the composite argument properties. All right, now if we just look for some common terms here to combine. Actually, before we combine things, we can see there's some stuff that will cancel out, right? I've got a minus sine of A times sine of B, and I've got a plus sine of A times sine of B. So these guys are going to cancel each other out. So I don't have to worry about those two. But the other stuff that's left is actually identical, so I actually have 1/2 out front. And since I have 2 of these guys, I've got the cosine of A, cosine of B, and another one sitting right here. I actually end up with 2 of them. So I can rewrite that as 2 times the cosine of A times the cosine of B. And the 2 times the 1/2, those will cancel each other out, and we're left with just the cosine of A times the cosine of B. And right there's our property. I started out with what I have over there on the right-hand side, just like we do to prove any other identity. And I've worked through to come up with what I have over on the left side, cosine of A times cosine of B. So there's our property. You can rewrite a product of cosine of A times the cosine of B as 1/2 the sum of cosines. All right, the other property, or the next property, I guess I should say, is this one right here. And like I said, I'm going to forego the proof of this because the proof is going to be basically the same here. I'm just going to simply say C above It's basically the same process there. But you've got the sine of A times the sine of B. And you can rewrite that as a negative 1/2. That's a little bit tricky because it's a negative there, but it's a negative 1/2. And then it's the difference of cosines. Unlike what we had up above there, where it was the sum of cosines, here it's negative 1/2 times the difference of cosines. And again, you'd start out with what you have over on the right-hand side if you were going to try to prove this. Use your composite argument properties. Things would cancel out very nicely, and you'd end up with what you see over there on the left. So that is our product of sum property for sine times sine. Sine of A times the sine of B. There are two other sum to product properties, and these are for sine times cosine, or cosine times sine is the other one. So if you have the sine of A times the cosine of B, you can rewrite that as 1/2 the sum of those two sines. 1/2 the sine of A plus B plus the sine of A minus B. And actually, now that we've already done this for the previous property there, we should have an idea how we're going to do this one. It's going to be the exact same way. So we probably could forgo the proof of it, but we'll prove this one and we'll skip over the proof for the next one because it'll be nearly identical. But start with what you have over there on the right-hand side. 1/2 the sine of A plus B plus the sine of A minus B. All right, and we're just going to use our composite argument properties to rewrite this. So keep your 1/2 out front. Sine of A plus B, we can rewrite that as the sine of A, sine of B, and then plus the, oops, I wrote that wrong. It's the sine of A times the cosine of B, plus the cosine of A times the sine of B. In fact, let me put that in parentheses here. In the case of addition here, I probably don't have to worry about distributing that minus sign through the second term, but definitely in the other set of properties, I'd want to make sure I have that in there. And now replace sine of A minus B with what it's equal to. And again, that's sine of A times the cosine of B, and then minus, it's the cosine of A sine of B. And again, if you look for stuff that you can combine here, first thing to notice is some stuff will cancel out. You've got a cosine of A sine of B here that's positive. You've got the same thing here, but it's negative. So these guys are going to cancel each other out. And the other two terms that you see left here, sine of A, cosine of B, sine of A, cosine of B, those are identical. So I can combine those two. Since they're identical, I can add them up, and I end up with two of those. So I've got 1/2 of 2 times the sine of A, cosine of B. And again, the 2 and the 1/2 will cancel each other out, and we end up with just the sine of A, cosine of B. There is our product to sum property for sine times cosine. And likewise, we have another property here, but this one is for cosine times sine. So if you have cosine times sine, you can rewrite that as the 1/2 the difference of two sines. 1/2 of sine of A plus B minus sine of A minus B. And again, I'm just going to say C above here, or you can even see the previous slide there if you want to see the proof of this, because they all are pretty much the same thing. Start with what you have over there on the right side, use your composite argument properties, and cancel out some stuff, combine some other stuff, and you'll end up with that property there. So those are the 4 product to sum properties. All right, so let's try using one of these in an example. If you turn to page 418 in your book, they say to transform this 2 times the sine of 13 degrees times the cosine of 48 degrees. Again, they've put the 2 out in front here just because that's how they're writing their property in the book, I think is why they're writing it that way. But again, I would probably rewrite this as 2 times this quantity of the sine of 13 degrees times the cosine of 48 degrees. This number out front doesn't always have to be 2. What are you going to do if it's 3 or 5 or some other number? You're going to deal with it the same way I'm dealing with it right here. Okay? So I think it's a more natural way to write this problem. If you just pull the constant out front, the coefficient, or pull that off to the side there in essence, and then deal with the product that we have here. So the property that you have there, we've got a product of sine times cosine. And remember, if you have sine times cosine, you can rewrite that as the sum of two sines, or really 1/2 the sum of two sines. So use your property. It's 1/2 of the sine of, it's the sum of the two angles here. So I've got 13 degrees and 48 degrees. Actually, let me just write it that way first, and then we'll deal with actually adding those together. You can do that in one step, but just so you can see how we're coming up with those numbers, let's write it that way. And then we add to that the sine of the difference, 13 degrees minus the 48 degrees. All right. Let's simplify this then. First of all, the 2 and the 1/2 out front, those guys are going to cancel each other out, right? Just like we've seen with those properties we were just going through and proving. And sine of 13 plus 48, we can add those two up. 13 and 48, 50, 61 degrees, I think is what we should end up with there. And then take the difference of 13 minus the 48 degrees, 13 minus, which would be 35, negative 35 degrees, I think there, negative 35 degrees. And actually, they said in this problem, transform it into a sum or a difference with positive arguments. So the 61 is good because that's positive. The 35, though, is negative, so he wants to get rid of that. And we actually have a property that tells us how we can deal with that. We have an odd-even function property. I'm going to write that off to the side here, that I have an odd property that says that since the sign is odd, I can rewrite that with an even, or sorry, with a positive value in there, not even, but a positive value. And I can replace the sign of negative 35 degrees with the opposite of the sine of 35 degrees. This is what it means to be an odd function. And then I can just rewrite this as a difference, and that's what I really have here. The sine of 61 degrees minus the sine of 35 degrees. And we should be able to grab our calculator and verify this if you want to. You could punch in what you have to start with, 2 sine of 13 degrees times the cosine of 48 degrees. Compare that with the sine of 61 degrees minus the sine of 35 degrees, and we should find we end up with the exact same result there. All right, that's an example using our product to sum property. All right, the other half of the story here is the other set of properties, which is the other way around. Instead of going from a product to a sum, switch that around, and you should be able to go from a sum to a product. So the sum to product properties. All right. Now the nice thing about these properties here, I know this is a lot to take in here, but we'll talk about this in a second. But the nice thing about these properties, once I've proven the product to sum properties, I should be able to just take that property and rewrite it to be able to go from a sum to a product and be able to do it easily. All right. The one thing that I don't like about the properties that we have written already is that to go from a sum to a product, you have to think of your sum as being either a sum or a difference of two numbers. That's not a convenient way to deal with those. So we're going to use the product of sum properties, but we're going to let x equal the a plus b and y equal the a minus b. So we're going to replace those arguments with the x and the y. And then you have to find out what does a equal and what does b equal. So if you add those two up, x is equal to a plus b and y is equal to a minus b. When you add those up, notice that the b's will cancel each other out and you'll be left with 2a. And so then if you solve that for a of course is going to be equal to 1/2 of x plus y. Again, all we've done is taken this equation that we see right here, and we're going to divide both sides by 2 or multiply by 1/2 to come up with this. If you do the same thing for the difference, when you take x minus y, take these two equations we have up above, when you subtract them, notice that time the a's will cancel out and be left with 2 b's. Since you're subtracting, that second b there, when you're subtracting a negative, it will become a positive, so you'll end up with a positive 2b. So now, if I take this equation here and I divide both sides by 2 or multiply by 1/2, you'll end up with this equation right here. B is equal to 1/2 of x minus y. So this tells me what I can use to make my substitution in the properties that I already know for a product to a sum. If I replace the a and the b with what I came up with, and I replace the a plus b and the a minus b with the x and the y, I should have my property here. So let's try this out. Here is the first property, and we'll go through the proof of this, but the proof is pretty much the work that we did up above here first, and just do the substitution. So here's the property first of all, the cosine of x plus the cosine of y. Again, the way I want to think of this is it's just the cosine of some number plus the cosine of some other number. That's the way I want to think about the sum to product property, so that way I can easily just substitute in a value for x and a value for y. And then over on the right, I can rewrite this as a product using those values of x's and y's. So it's a little more complex there, but it's 2 times the cosine of 1/2 the sum of x and y times the cosine of 1/2 the difference. Again, the sum of 2 cosines here turns out to be the same as 2 times the product of 2 cosines to go from a sum to a product. All right, so let's just write down what our property is that we already have from a product to a sum. And let's do the substitution here. So let's do that. Let's write down our property that we already proved here on the previous slides. Let's do the cosine of a times the cosine of b. And that was equal to, remember it's equal to 1/2 the sum of 2 cosines. So 1/2 the cosine of a plus b. And then plus the cosine of a minus b. All right, very nice. That's the property we've already proven here. And now we're going to do the substitution that we've described up above here. So these two, actually 4 substitutions here. I'm going to replace the a that I see in there. I'll circle that. I'm going to replace this a with what I've marked in red up there. A is equal to 1/2 x plus y. I'm going to replace the b with that. And for the other 2 quantities here, I've got x is equal to this. So I'll replace the a plus b with x. I'll grab one other color here, I guess. Grab that orange. And I've got y is equal to a minus b, and I'm going to replace the a minus b with that guy. Okay, so I'm just going to do a straight substitution is all we're going to do. We've kind of done the hard work up above here. We just have to do our substitutions now. And I should see my formula just show up here as a result. So a again, I've got the cosine of, a again is equal to 1/2 of x plus y. And cosine of b. So b we said is equal to 1/2 the difference of x and y. And then over on the right side, this is equal to 1/2 of the cosine of a plus b. A plus b, we said that was equal to x, so this is the cosine of x. And a minus b, we said we're going to let y equal a minus b, so this is plus the cosine of y. So there's our substitution. That's not quite the property that I have up above yet, so let's get rid of the 1/2 that I see over here on the right-hand side, multiply both sides by 2. And actually, I'm going to write, I guess I'll leave it in the same order that I have it in here, but let's move the 2 over here. So I've got 2 times the cosine of 1/2 of x plus y times the cosine of 1/2 of x minus y, and that's equal to the cosine of x plus the cosine of y. If you want to switch the sides with those 2, you'll see that you end up with this property that we have right up above there. Very nice. So there is our sum to product property. I can rewrite cosine of x plus cosine of y as 2 times the product of 2 cosines. Similarly, we can do the same thing here with a sum to product property for the difference of 2 cosines. Again, I'm going to say for the proof here, just see above, the same process that we just went through is the same technique you're going to use here. Replace the a and the b with what we calculated up above, replace the a minus b and the a plus b with what we initialized for x and y, and substitute. You're going to get the same result here. But if you have the difference of 2 cosines, cosine of x minus the cosine of y, you can rewrite that as a -2. Again, this is the one property that had that weird -1/2 that showed up for the product of some properties, so that negative is still here. -2 times the product of sines. -2 times sine of 1/2 of x plus y times the sine of 1/2 of x minus y. That is our sum to product property there for the difference of two cosines is a -2 times the product of sines. All right, for the last two properties here, at this point we should already understand that we're going to go through this in a very similar way. You probably don't need to rewrite this down here. I'm just putting it on the slide again here for you just so you realize that we're going to do the exact same substitution for the other two properties. Okay, so x is still a plus b, y is still a minus b. We have to add those two up to find out what a is equal to. We take the difference, we find out what b is equal to, etc. Okay, so that's the exact same. Let's talk about the two properties then. And we'll prove the first one. And it will be a very similar process then that you'd go through to prove the second one. So here we've got the sum of two sines, sine of x plus the sine of y. And again, to prove this, you're going to start out with the product to sum property that states this exact same thing here. So the product to sum property that we're going to use is starting out with the product of sine and cosine. So I've got the sine of A times the cosine of B. And so for the sine of A times the cosine of B, we said that that was equal to, you can rewrite sine times cosine as the sum of two sines, which is what we see over on the left side of this property we're trying to prove. This is equal to the sine of A plus B, and then it's plus the sine of A minus B. All right, oops, it's 1/2 that. 1/2 that quantity. That was our property. Okay, and again, the same technique that we just did on the previous slide to prove this, we're just going to do a straight substitution to make this happen. So for A, we're replacing A with what we calculated. That was going to be 1/2 of x plus y. For B, same story, replace it with what we've calculated. It was 1/2 of x minus y. So that's the left side of this. This is equal to, squeeze my 1/2 in there, 1/2 of, and then on the right side here, A plus B, we defined that to be what x was going to equal. So this is the sine of just x. And then A minus B, that's what we defined y to be equal to, so I'll replace that with y. All right, now let's move the 2, or the 1/2 really to the other side there, like you see up above. So I'm going to multiply both sides by this 2 that we have here, or by this, we're going to multiply by 2 to get rid of that 1/2. So I'll end up with 2 times the sine of 1/2 of x plus y times the cosine of 1/2 of x minus y. And that's equal to the sine of x plus the sine of y. There's our property that we have up above there. I've just got, I guess the sides flip-flop there. If you want to rewrite it, you certainly can. But you now have a sum over there on the right-hand side. The sum of x and y, the sum of the sine of x and sine of y is equal to 2 times this product of sine times cosine. And for the very last one, again, I'm going to forgo the proof of it, but we can write it down at least. Here's the last property here that we've got, which is the sum of, actually it's the difference of sines here, sine of x minus the sine of y is equal to 2 cosine of 1/2 of x plus y times the sine of 1/2 of x minus y. So you can rewrite the difference of sines as 2 times the product of cosine times sine. And again, for the proof, I'll just say see above or see the previous slide. Same technique, so repeat it. All right, let's take a look at a couple of examples here. Look at example 2 there on page 418. And it says to transform the cosine of 7 theta minus the cosine of 3 theta into a product of functions with positive arguments. So we're trying to go from a sum, or really in this case it's a difference, of cosine. So we've got the cosine of 7 theta minus the cosine of 3 theta. And we want to rewrite this as a product. So again, go back through your properties there. I'm going from a difference of cosines. This is the one that you can rewrite as the negative 2 times the product of sine. So I can just use my property here. This is equal to a negative 2 times the sine of, and I'm going to go ahead and write this out. You can kind of simplify this as you go, but it's 1/2 of 7 theta plus 3 theta. That's how we're going to come up with that argument, 1/2 the sum of those two. And then we multiply that by the sine of 1/2 the difference of those two. So 1/2 of 7 theta minus 3 theta. We'll put another set of parentheses there. And now simplify this thing. We've got a negative 2 times the sine of 7 and 3 is 10. Half of that would be 5 theta. And 7 minus 3 would be 4 theta. Half of that would be 2 theta, sine of 2 theta. So we end up with the difference of two cosines can be rewritten as negative 2 times the product of sines. All right, one last example here to kind of illustrate or tie back into what we saw in the very first example that we started out with. That here I've got a sum of two sinusoids here. I've got a sinusoidal axis that looks like it varies. And they want us to find the equation of this. If you look at example 3, it shows the graph of a periodic function with a variable sinusoidal axis. Using harmonic analysis, find the particular equation of this function as the sum of two sinusoids, and then transform that sum into a product. All right, so we can go through that. You sketch the sinusoidal axis that goes through here. Really, I only have to go to pi, but if you want to go out to 2 pi, you can, because after pi, you have one full period of this thing. So let's call that y1. The amplitude is 1. It looks like the sine function, and the period of this is pi. So I can rewrite this as, I'll write it as 1 times the sine of 2 pi divided by pi times x. And then let's just rewrite that. This is how we come up with the equation, and now let's simplify it. We have sine of just 2x then for that guy. And then for the other function, I think we can quickly go through and find out what y2 is equal to. I'd say that this looks like we have an amplitude here of just 1 unit. And for the period of this thing, we got to count up the number of cycles we see here. There's 1, here's 2, there's 3, there's 4, and there is 5 in the interval from 0 to pi. Actually, it's technically a little bit past 0 and a little bit past pi. There's really what we're looking. But there's 5 cycles that I see there. So I can come up with the period now for that. And if you look at what's happening right here at the y-axis, it looks like we're crossing the sinusoidal axis there, and we are increasing from there. So that looks like it's a sine function. So from that, we should be able to get our equation. We have 1 times the sine of, it's going to be 2 pi divided by our period. So we took the interval from 0 to pi, and we divided it into 5 parts. So the period is pi over 5 is what we'd have there, times our x. And that, of course, will simplify. The pi's would cancel each other out. And you have 2 times 5, that's 10. So this would be the sine of 10x. So I guess putting all that together, we know it's a sum of these two because it's a sinusoidal axis that varies. So we have y is equal to the sine of 2x plus the sine of 10x. So that was the first part of the question, was find the equation of this. Use a harmonic analysis to do that. And now for the second part of this problem, what we want to do is we want to be able to come up with the product of these two. That is, use your sum to product property to rewrite this. So we've got, maybe I should rewrite it down here. We've got y is equal to the sine of 2x plus the sine of 10x. So if you have the sum of two sines, you can rewrite that as 2 times the sine times cosine is how we can rewrite that. Just use your property that tells you that you can rewrite the sine of some quantity plus the sine of some other quantity. That's the property we're using, sum to product. So this is equal to 2 times the sine of 1/2 of the sum of those two, 2x plus 10x. And then times the cosine of 1/2 the difference, 2x minus 10x. And now let's simplify this here. So we have the 2 stays out front. I've got 2x and 10x. That sounds like 12x. Half of that is 6x. So it's the sine of 6x. And then 2 minus 10, that's a negative 8. Half of that is a negative 4. So I've got the cosine of a negative 4x. And I would suggest you probably want to get rid of that negative there. Again, use your even property here. This here is an even function, so we can use that even property. That says I can rewrite the cosine of a negative value as just the cosine of that value. You can get rid of the negative sign there since it's an even function. So it's 2 times the sine of 6x times the cosine of 4x. And I will leave that to you to sketch that to verify that in fact you get the same graph that we started with, but there is our sum to product property. All right, that is the end of this section.